All right, in this lesson we're going to learn about intermolecular forces. What are they and how do they affect the physical properties of substances all around us? So by the end of this lesson you should be able to tell between inter and intramolecular forces. You should be able to know what impact those forces will have on surface tension, boiling point, melting point, and vapor pressure. All right, let's get started. Now, before we actually dig into it a little bit, I do want to remind you that this is in the textbook, chapters 8. Towards the end, you can see the sections there, and also chapter 10, just the very beginning, where it'll walk through the different kinds of intermolecular forces. But this lesson is not about the kinds of intermolecular forces. That's for the next lesson. What we're going to be digging into here is just what are they and how do they impact physical properties. Okay, so what are intermolecular forces? They are forces that are between molecules. So not within a molecule, they're not bonds, right? You have covalent bonds, you have ionic bonds. You're going to see in this unit, because we're looking at molecules, we're going to be focusing mostly on covalent bonds. But what I want you to do in here is I want you to label which of these bonds are covalent bonds and which of these are intermolecular forces. And maybe we'll just do this first one here. I have 1, 2, and 3. Which of those are covalent bonds and which of those are intermolecular forces? All right, so hope you saw that definitely the bond between the two chlorines is a true covalent bond. It's quite strong. I don't know, I don't have the chart in front of me at the moment, but very often covalent bonds can be, kind of around the 400 kilojoule mark. Now, we have not done thermodynamics yet, but kilojoules is a measure of the energy it takes to break that bond. So that's a typical covalent bond sort of energy. Even the strongest intermolecular forces tend to be less than about 20 or 30 kilojoules per mole. So they're significantly weaker, and some of them can be down less than a kilojoule per mole. They're very, very, very weak interactions, but they're incredibly important interactions. So the key thing here is, let me get rid of my eraser here. The key thing here is that intermolecular forces are the forces between bonds, kind of like international flights are the flights between countries, right? But if you're flying within the United States, that's not an international flight, right? That's within the country. We call it domestic, right? Or we could call it an intranational flight because it's within the country. So that's what those prefixes mean. Inter means between the two groups. Intra means inside the country, the molecule, whatever it is you have. So therefore, intermolecular forces are attractions between two molecules, and intramolecular forces are covalent bonds. Now, I'll tell you in practice in chemistry, we don't really refer to bonds as intramolecular forces. But my point being is when you're writing about intermolecular forces, you have to be very careful and make sure you don't flip it. It's always intermolecular forces because those two prefixes mean pretty much opposite things. All right, so now that we've got the prefixes down and we've got that general idea, I want you to look at this potential example here, which is I want to know if you have some water in here and you're boiling it, you put it on a stove and clearly you get some steam, what's really breaking there? Is it the covalent bonds, the O and the H, or is it the intermolecular force? What do you think? Well, there's some evidence to what's going on here. If you stop and think about water as a liquid, right? It turns out that the only thing that's happening is water is still a molecule. You haven't broken a single bond. You're just turning it into a gas. Well, think about what the consequences would be if you were actually breaking covalent bonds. Here you're just separating water molecules, but if you were to actually break covalent bonds, you would be turning this into hydrogen and oxygen. You'd be breaking those OH bonds and turning them into hydrogen and oxygen gas. Now think about that for a second. All the time when you get into the shower, if it wasn't just simply the molecules separating, like say for instance this, right? Here's liquid water and it evaporates away. They're still water molecules. They just are sort of leaving each other. They're letting those weak intermolecular forces break, not the bonds. Because if you were in a shower and the shower steam was evaporating and you were actually breaking bonds, it'd be a way more dangerous situation because then you'd be making hydrogen gas and oxygen gas, and that would be way more dangerous. Think about it, like you couldn't even smoke in the shower anymore. Not that we should ever do that. But if you did try to do it, it'd be way more dangerous. But it's not dangerous because the gas around you is not explosive. It's not like those two, right? It's just water vapor that if you let it cool down, it'll just condense right back into water. So all you've done there is break the intermolecular forces, not the actual covalent bonds. And why? Because as we saw in the previous slide, it would take way more energy, 10 times the amount of energy, to actually break covalent bonds. So these are very weak interactions, but they're important interactions. All right, let's get rid of that and let's go on to here. Now, if you look at these two, I love these two diagrams here. Which gas do you believe, why did it stop? Which gas do you believe is representing intermolecular forces within the gas? The red one or the blue one? Well, when you look at it, they're representing different gases. But the one on the left, there's far more intermolecular forces. You can see the molecules sort of glomming onto each other like that. They're temporary. They can be easily broken. You can see they go on and sort of get attracted to another gas particle. They come and they go. They're not like covalent bonds where they stick together fairly permanently, right? But if you look at the gas on the right, the blue one over here, there's no attraction to the other molecules at all. Now know that all gas particles, well, all substances, have some sort of intermolecular forces, which I like to call sticky forces, right? They just make the molecules a little bit sticky. There aren't any real substances or gases that don't have any intermolecular forces, and we have some evidence for that. If you cool down any substance, even helium gas or hydrogen gas, at some point it will condense. Because you remember, at absolute zero, all substances are crystalline solids. You can make solids out of all of them. And if they didn't have any attractive forces like these don't, then they would never have any reason to stick together in the way that the red particles are. Because sticking together is what causes gases to condense or liquids to become solids. All particles have some intermolecular forces. Oh, before we go, by the way, which one, the red one or the blue one, do you think is more likely to represent an argon molecule? Now, I shouldn't have said argon molecule because argon's not really a molecule. It's one of the few gases that is not diatomic, like oxygen or nitrogen. That's what the blue ones would represent, right? Over here, this might be gases that are all noble gases. Neon, argon, krypton, because they're not diatomic. Anyway, I hope my misspeaking didn't head you down the wrong path there. So if we know that they're sticky forces, then why are they so important? Why are we going to spend so much time doing this? Let me make myself smaller. So, why are they important? Well, it's because, as I said, if there were no intermolecular forces, all compounds would be gases. So therefore, since all compounds have some intermolecular forces, their physical properties are going to be impacted by the strength of those forces. So we're going to be looking at, how do I know if an intermolecular force is strong? And furthermore, will it affect the boiling point of the liquid, the melting point, the vapor pressure, and the surface tension? So those four things. So we're going to walk through examples of those four things. Let's look at this for a second. So we've got the boiling point here of a couple of different substances at STP. You can see that we've got bromine boils at 58 degrees Celsius at standard temperature and pressure, whereas chlorine boils at negative 34 degrees Celsius at STP. What I want you to predict, and don't worry about being wrong here, but I want you to predict which of those two molecules must have stronger intermolecular forces. So definitely bromine would have the stronger intermolecular forces. There we go. Bromine would have the stronger intermolecular forces. Why? Because its boiling point is higher. What that means is, you can imagine at 0 Kelvin, everything's a crystalline solid, right? That would be true for both substances and all substances. But as you warm it up and warm it up and warm it up, you can see that chlorine turns from a liquid to a gas earlier, which tells you it took less energy to get those two particles to separate and go their own separate way. That must tell you that this intermolecular force is pretty darn weak between chlorine particles. Whereas look how much longer bromine hung on to a much higher temperature. That means those attractions must be significantly stronger. Now, a couple of things that I should point out based on these diagrams that I'm drawing there is this idea of drawing dashes for intermolecular forces. It's not really an accepted thing. But you're going to see me use sort of thicker dashes to represent stronger bonds, stronger intermolecular forces. They're not real bonds, right? And sort of thinner ones to represent weaker ones. But it's not an accepted approach. It's just kind of to give you a visual. Now, the other thing that's going to come out of this too is, well, why? Why is the intermolecular force between bromine significantly stronger than chlorine? You notice we haven't said that yet. But clearly the data, the fact that bromine boils at a much higher temperature than chlorine does, it gives evidence that its attractions between its molecules must be significantly stronger. I hope you didn't mind that I converted those temperatures to Kelvin, right? Did you catch that? Just did that beforehand to make things go a little bit quicker. All right, let's try one more. So let's make a prediction here. Let's do melting point. So now we're talking solids turning to liquids. If argon, the gas, has a melting point, which, look at that, it implies argon can be a solid, right? And a liquid, pretty cool. If you've ever wondered at what point does it melt, negative 189 degrees Celsius, which you could convert to Kelvin, might be easier to deal with. And helium's melting point is negative 272. It's kind of interesting, right? So what I want to know is, based on those pieces of physical data, which of those two substances must have stronger intermolecular forces between their molecules? So clearly the answer here is that argon has significantly stronger intermolecular forces. Definitely heliums are weaker, and you can see why. If you convert these to Kelvin, and you can see me hinting at converting them to Kelvin makes things much easier to visualize. Negative numbers they can get you turned around a little bit, right? So if everything is a solid at absolute zero, crystalline solid, that means that helium melts at 1 Kelvin, right? That's 1 Kelvin. It's essentially right away where it turns from a solid to a liquid. It sort of breaks those intermolecular forces between helium particles. And look, I'm going to draw it more appropriately. Helium is just an individual molecule, right? It's not diatomic. So two helium particles must have a very, very, very weak attraction between them. Whereas look how much longer argon can hold on to much higher temperatures. Argon must have much, much, much stronger intermolecular forces between argon atoms. And remember, that's not a covalent bond. This is not a diatomic molecule. It's just the loose intermolecular sticky forces, as I like to call them, between two fully separate particles. All right, so that gives us a feeling for how boiling point and melting point can give us a hint as to how strong the intermolecular force is. The other thing before we go on, because we're going to do some writing about intermolecular forces, yes, IMF is a perfectly acceptable abbreviation if you don't want to write it out, because it is kind of a long phrase. But that's how boiling point and melting point can help you predict which has stronger intermolecular forces. All right, let's keep going. Now, so part 2, vapor pressure, in your notes. You know what vapor pressure is, but I want you to make a prediction. You can see over here, I've got a gas with much higher vapor pressure, right? Like if I tried to hold the jar on the lid, it would be harder to hold on here than it would for a substance that had low vapor pressure, right? And I will tell you, generally speaking, water has pretty low vapor pressure. But that's beside the point. So what I want to know is, do you believe that substances with low vapor pressure or high vapor pressure have stronger intermolecular forces? Make a prediction. Okay, so the answer is definitely that substances that have low vapor pressure have stronger intermolecular forces. Why? Because they're having troubles evaporating. And the reason they must have troubles evaporating is because they have very strong intermolecular forces between all of those particles, right? Whereas ones that evaporate easily and therefore have high vapor pressure must mean that those attractions are very tenuous, they're very weak. And so it's easy to convince them without very much heat to evaporate and create high vapor pressure. So that's the relationship between vapor pressure and intermolecular forces. Let's look at this one. Make a prediction here. Based on my diagrams and my silly drawings, which you know those dashes aren't official, but which do you think, molecule A or B? Which one of those two would evaporate the fastest? Definitely molecule B, because molecule B has weaker intermolecular forces, and therefore it would have less attraction, and they'd be more likely with very little energy to turn into gases. Stronger intermolecular forces evaporate slower. Now, our last example is surface tension. So surface tension is where, like, probably the most common example of it is when you look at your windshield, right, you will see that the water doesn't spread out very evenly when it rains. You'll get these little droplets, right? And what's happening in those droplets is the reason they're sticking together instead of just going and going flat is because all of the particles are very strongly attracted to each other. And so they sort of pull each other into this little bit of a droplet. Whereas if you look at things that have very weak intermolecular forces, they don't. So things that have high surface tension tend to have strong intermolecular forces. All right, now the last thing we're going to do here to finish up, since we now know the relative strength of intermolecular forces and how they affect boiling point, melting point, vapor pressure, and surface tension, is all of these things involve phase changes, right? It's phase changes that are impacted by intermolecular forces. So we've got to make sure you've got them all. So what I want you to do here is I want you, in your notes, to see if you know all of the appropriate phase changes so that you have the language that you need here. In other words, a liquid turning to a gas, well, that's evaporation. Or you could say boiling. I'd accept either one. What I want you to do is fill out all the others and see if you know them all. Okay, so a liquid turning to a gas is evaporation. Obviously a gas, like in the shower, right, you've got water steam around you. It can condense into a liquid. Most of these aren't very challenging, right? A liquid turning to a solid, that might be freezing, so like ice freezes, right? Melting, this is the sad way, right? This makes everybody sad because that's what happens to our ice cream. Our somewhat solid ice cream turns into a liquid and makes us sad. And then probably the hardest one is to know is just what happens when things go directly from solid to gas. Like say, for instance, if something sublimes, right? It does sublimation. Good example of that is solid CO2 will turn directly to gaseous CO2. It sublimes, and that's dry ice, right? Dry ice is CO2. If you go the other way, which is the way they make dry ice, and you take gas and you turn it into a solid, it's referred to as deposition, which is a fancy way of saying, maybe the verb way of saying, depositing, right? A gas particles are depositing into a solid chunk. Yeah, so those are all of the phase changes. Now, we're going to be talking throughout this unit a little bit about the types of energy required to break intermolecular forces and to make these phase changes occur. Like if you go from a liquid to a gas, we're talking about this change, and it turns out actually it doesn't matter whether you're talking about going from a liquid to a gas or backwards, gas to a liquid and condensing. That's referred to as the heat of vaporization. Heat of vaporization, and it's referred to, it symbolically is delta H with a little VAP. In other words, there will be a number here. I don't know, don't write down this number because it depends on the substance. It might be like 200 kilojoules, right, per mole or something like that. Don't write that down because it depends on the substance. And if you're going from a solid to a liquid, these, which doesn't matter which way you're going, whether you're freezing or melting, is referred to as the heat of fusion. A little bit of a surprise there, right? But you can imagine that a liquid could fuse into a solid. So it's referred to as the delta H of FUS, fusion, right? And it also has some number. And that number will be positive if you're trying to go one way because you have to add heat in one way and you get heat back the other way. But you'll see those terms show up a little bit. The heat of fusion and the heat of vaporization. All right, great job. Let's do a little checking to see if you understood the goals for today.